What's the purpose of a graph? Why do we use them?
To display a range of information in like a way that's easy to understand, that shows everything that we need to know, and it's not complicated.
Right. It's basically a way for us to concisely and visually demonstrate the relationship between two things. Okay? It shows a lot of data in a concise form. Okay? So even if I don't know a whole lot about the effect of temperature on photosynthesis, if I look at this graph, can I learn a fair amount about the relationship between temperature and photosynthesis?
Yes.
Even if I have no background in that, right? Okay, so I can see from this graph that photosynthesis increases until about 30 degrees Celsius, and then it just falls right off. Okay, so, all right, I can see that that's the relationship between temperature and photosynthesis. So I don't have to read some really, really long, complex research paper about the biochemical processes that go on inside the chloroplast to know that as temperature goes up, photosynthesis goes up until about 30 degrees and then it just falls off. Okay? So that's the purpose of a graph, is to concisely show the relationship between the manipulated variable and the responding variable in an experiment. In this experiment, what would the manipulated variable have been?
The temperature.
The temperature. Manipulated variable always goes on the x-axis on the graph. Okay, always. Because we want to be able to see what effect it had on the responding variable. So the responding variable always goes on the y-axis. Okay, now, is there anything kind of, let's say, missing or bad about the format of this graph?
The rate of photosynthesis, the number goes way up to 400, even though the real rate, it only really goes up to 200.
Yeah, they probably could have made better use of the space on the y-axis. They went quite a bit higher than they needed to. This probably could have been a bit more detailed or accurate if we'd have only gone up to 250 maybe. Okay, or maybe even 200. It looks like we could have gone right to the top of the graph. Okay, so I would say that's one thing. What else?
We don't know what the 100, 200, 300, 400 imply when it says rate of photosynthesis.
Yeah, there's no units. That's a big mistake. Okay, when you put stuff on a graph, you need to put units on the graph. I have no idea what the units for the rate of photosynthesis are. Okay, I don't know if they're milliliters of oxygen per minute or hour, or if it's milligrams of glucose produced. Like, I have no idea what those numbers are. I just know the rate goes up, okay? But I could know a lot more if I knew what those units were, okay? So you should always have units on your graph, okay, on each axis. We can see that the temperature here is in degrees Celsius, okay? Not degrees Kelvin or something, or Fahrenheit or whatever, okay? We know for sure what the units are. So a good graph has a title that is explanatory for what's on the graph. Generally, we go, X versus Y, okay, generally. And then each axis is labeled, so we know what's on it, and each axis has units, so we know how we're measuring that particular variable. The other thing that's important is scale. We're lucky, we don't have to make graphs by hand anymore, okay? Like, when I was your age, graphs were drawn by hand, okay? Which means you had to figure out your scale for both your y and your x-axis. So you had to go, okay, count how many lines I have, and know my biggest number is this number, so divide this number by the number of lines, and then I'll know what each line should be worth, and then I have to write out my scale, and every single line I have to denote what it's worth. Okay, well, that was a pain in the neck. Not to mention that you had to plot all the points and go, okay, so when x is 5, y is 200, yeah, okay, like it was a pain in the neck. Okay, to do it all by hand. Now you just plug it into Google Sheets and it spits the whole thing out and decides on the scale for you. Does it always do a great job? No, sometimes you have to correct it. Okay, and we'll go over that tomorrow. Sometimes it picks the wrong kind of graph. Okay, it draws like a pie chart when you want a scatter plot. Okay, it just doesn't always pick the right one. Okay, so we'll be looking at that kind of stuff. But the big thing here, guys, is what does a graph have to have? It's got to have a title. It's got to have scale. It's got to have labeled axes with units, okay? And you got to make the best use of space possible on the graph, okay? That is definitely a mistake here, okay? The thing goes all the way to 400 and we don't have a number over 200, All right, questions on that? All right, so what we're going to do is we're going to look at our first type of graph. Okay, and our first type of graph is a graph of position versus time. So our lab on Wednesday is going to involve us doing something like this. I'm going to take a measuring tape and I'm going to string it out along the floor of the atrium. We're going to go out there with little battery-powered electric carts, okay? And we're going to run the carts, and every 5 seconds, we're going to mark on the measuring tape with a sticky note where the cart was, okay? Every 5 seconds, we're going to mark where it is. In that lab, what should go on the x-axis? Time or position? Time. Now, sometimes people have a problem with that when I say this. Time is the manipulated variable. Can you manipulate time?
No.
No.
Yes, you can.
Time travel?
You are deciding that you are going to record the position of the cart every 5 seconds. Therefore, you have manipulated not only how often, but for how long the experiment will run. You're not making time run slower, faster, forwards, backwards, okay? You're just determining the intervals. In that way, that is a manipulation of time, okay? Because we have decided how often and for how long the data will be recorded, okay? That counts as manipulating time.
Question, are we allowed to bet on the cards?
No, we cannot encourage gambling here, okay? All right. Plus, it's very obvious which ones are going to win once you turn them on. Okay. Okay. So time is going to go on our x-axis. In fact, for most of the things we do, if time is involved, time is the manipulated variable, because it's very difficult to measure whether time responds to anything. Right? If time were to respond, that would mean it would have to be running differently than it normally does. So time is pretty much always going to be our manipulated variable when time is involved. Okay? And that's simply going to be the result of us choosing what our interval will be, our recording interval, and for how long the experiment will run. All right, so we are going to look at what kind of information can be read from our kinematics graphs. Okay? We're going to look at how the equations that we've been using, namely v equals d over t, is actually derived from a graph. Okay, we'll look at that today. Okay? And the kinematics equations and graphs basically show the same thing. So some of those questions that we did last week, we could easily draw a graph of, okay, and kind of get a better idea of what was going on. Okay? All right, questions so far? All right, so a position versus time graph shows where the object is at various points in time. Okay? Position is where you are. Okay? So on this graph right here, okay, the one on the left, thank you. Okay? Where do I start? What's my starting position?
20 meters.
Yeah, positive 20 meters. Okay, but yeah, 20 meters is my starting position. For the first second, what is that object doing? Nothing. How do we know that object is doing nothing?
Because it's at the same position.
Right. At time 0, it's at a position of positive 20 meters. At time 1 second, it's still there at a position of positive 20 meters. That means, it may not have done nothing. Maybe it was dancing in place, I don't know. But it didn't move, okay? It didn't change its position during that second. Okay, so what is it doing between 1 and 3 seconds? Okay, in what way?
Accelerator?
Is it going faster?
No.
Okay, that's our gut go. Like, I get that answer every single time because our gut reaction when we see a line going up is faster. Okay, but in this case, it actually isn't going faster. Here's why. Okay, in this first second, it went 20 meters. And in the next second, it also went 20 meters. Does it go in the same speed?
Yes.
Yes. Okay, so in this graph, what we're seeing is that the position is changing at a uniform rate. In other words, it's traveling at a
Set speed.
or constant velocity. Yeah. Okay, it's traveling at a constant velocity of, in this case, 20 meters
a second.
per second. Okay, everyone kind of follow the interpretation there?
Would it truly be velocity because we don't get a direction?
I said positive. And we do have a direction because we know it's going this way. Yeah. Okay. Because I gave positive earlier, yes, I can say velocity, traveling at a constant velocity. Okay? Because if you're traveling at a constant speed, you are also traveling, in this case, at a constant velocity. Okay, so what's the object doing between 3 and 4.5 seconds?
Standing still.
Standing still, staying at the same position. What is it doing between 4.5 and 6 seconds? Going backwards. Still constant velocity?
Yes.
In which part is it going faster? Between 1 and 3 or between 4.5 and 6?
4.5.
How do you know?
Because it moved further in a shorter amount of time.
Actually, it moved the same distance in a shorter amount of time. Okay? Does that mean you're going faster?
Yes.
Absolutely. I mean, that's how you win a race, right? You're running the same distance, it's who finishes first. Okay? That means who was the fastest or shortest time. Okay? So yeah. Now, in this one here, we know it's faster for that reason, but is there something about these lines that can also tell us one is faster than the other?
The second one is steeper than the first.
Right. The second one is steeper than the first. Okay? So the reason we're going over this, guys, is this is exactly the kind of thing I would ask you on a multiple choice question. Okay? I would ask you to interpret the data from the graph. Okay? Be able to look at this graph and tell me exactly the things I've just asked you. What's going on in the first second? A, the object is accelerating. B, the object is moving backwards at a constant velocity. C, the object isn't moving. D, the object is moving forwards at a constant velocity. Okay? Just being able to analyze the graph by looking at it is one of the most important skills that we can have in physics. Yeah. Okay? All right. Well, let me ask you a different question. What is the total displacement of the object between 0 and 6 seconds?
0.
How do you know?
Does it move back to seven?
Oh, that's good.
Because he ends up at the same position.
Right. His initial position and his final position are the same position. Okay? This is a formula we haven't talked about very much. Okay? But we can calculate displacement by doing exactly that. And we do it on a graph all the time. Displacement is your change in position. So if I take my final position and subtract my initial position, I will get my total displacement. Okay? And in this case, that's 20 minus 20, so I get 0. Okay? What's the velocity of the object between 4.5 and 6 seconds? What's our formula for calculating velocity?
Distance over time.
Not distance.
Displacement.
Displacement. Okay, so if velocity equals displacement divided by time, and this is how I calculate displacement. Can I get these 2 points off of my graph? Can I get the time off of my graph? Okay, so what I would do is I would say final position, 20, minus my initial position, 60, divided by 1.5 seconds, right? We're going from 4.5 to 6. That's 1.5 seconds.
Is that really 4.5? I thought it was like 4 seconds, 5 seconds. Oh.
4.5 seconds.
That makes more sense.
Okay, cool. All right, so 40 over 1.5. I don't know what that comes out to. 30? I feel like that's the right answer, but I don't know. It is? Someone punch it in? It's Monday, and I don't trust my math brain. Yeah, I mean, it makes sense, 40 divided by 1.5. Nope, see, there we go. 27. Okay. What do I need to put in front of that 27 meters per second?
Backwards.
Yeah, because when I go 20 minus 60, I actually get negative 40. So my velocity is negative. We did say before that the object was moving backwards between 4.5 and 6 seconds. So my velocity does need to be negative because velocity is a vector quantity and because I got a negative number when I calculated my displacement for that problem. Okay? Is this basically what we were doing last week with word problems?
Mm-hmm.
Okay. It's not any harder. In fact, it's probably easier because you don't have to do any reading column. You just have to look at the graph and get the numbers. Okay? That's the purpose of a graph, to make those kinds of interpretations and analyses easier. Okay? All right. In the second graph, what is that object doing? That object is accelerating. How do we know? It's curved. Okay, what else?
It's traveling like even more further every second.
It's going further every second. Okay, and I don't mean further in that, you know, this went 20 and then that was 20, that's further. I mean it's actually, its displacement the next second is greater than it was in the previous second. The only way you can go farther in the same amount of time is to go faster. Okay, so just as a demo here, in the first second, the object only goes that far. Okay, but in the next second, it goes that far. And then the next second, that far. And we can see clearly that the distance traveled every second is getting bigger and bigger and bigger. Okay, so we see a curve when an object is increasing something in a non-uniform way. Okay, on this type of graph, that means the object's velocity is increasing because its displacement or position is changing in a non-uniform way. And what we mean by that is exponentially. Okay, everybody with me there? So if I show you a picture of a graph, that's the kind of interpretation I expect you to be able to do. Now, here's the trap I don't want you to fall into. I don't want you to memorize what all the shapes mean. Okay? When we went through all of this, we analyzed and broke down every part and interpreted what they meant. That's the skill I want you to take away, is being able to interpret any graph. Okay? If you memorize every graph, that might work for Science 10. We're only going to have a couple of graphs. Then you're going to get to Physics 20 and we'll have a dozen graphs. Then you're going to get to Physics 30 and you could have 4 dozen graphs. It's going to be pretty hard to memorize what every shape means on all 50 graphs that you could have in Physics 30. What's better is to be able to interpret any graph. Okay? And all you have to do is look at what's on the graph and ask yourself, what's happening here? Oh, well, it's going further each second than the second before because this is showing me position. In order for something to go further, it has to go faster. That means it's accelerating. That's the kind of interpretation I want you to do rather than a curve means acceleration. Okay? A curve only means acceleration on this graph. Okay? A curve means something else on other graphs. Okay? So that's why I don't want you to memorize it. You will definitely get them confused. Okay? I see that happen all the time. I can always tell in the unit exam who's interpreting and who's memorizing. Okay? There's like 2 questions that a memorizer will always get wrong. Okay? So make sure you're interpreting each graph. That's the skill I want you to practice. Okay? Okay. Now, slope calculations. How many people have done slope calculations in math already? Okay. I beat math to this. Okay. All right. So here's what slope means. Okay. Slope is essentially the rate at which the line rises divided by the rate at which the line runs. Okay? So basically, how steep is the line? That's what slope is. On every graph, slope represents something. Okay, that something is different because every graph has different stuff on it. Okay, so this is again a spot where I don't want you to memorize the slope on this graph means this and the slope on this graph means this. I want you to be able to look at a graph and go, okay, I've got this and this. That means the slope will represent this. Okay, be able to interpret it rather than memorize it. Okay, on this graph, this is a position versus time graph. Okay, so we got position on the y, we got time on the x. Okay, so if I'm looking at the rise is telling me how much the position changes. Would you agree? Since the position is on the y. Change in position equals, starts with D, displacement. Okay, so on this graph, the rise would be, okay, if I wanted to calculate the rise, I would take this value here, that would be my final position, and I would subtract, in fact, I'm going to change this up just a little bit here. I'm going to make this line just a little longer. Whoa, that's not what I wanted it to do. Okay, so I'm going to take that there, that'll be my final position, and this will be my initial position. Okay, would the rise be the difference between those two numbers?
Mm-hmm.
Right, so in other words, the rise will be final position minus initial position. Okay, what's the run-in? What's on the x-axis? Time. Okay, so doesn't this equal this is where v equals d over t comes from. Okay, that formula you've been using for over a week is the slope of a line on a position versus time graph. Okay, does everyone follow how I got to that? Right, I took my change in y, which is how I calculate any slope. I take the change in y, the rise, and I divide it by the change in x, the run. On this particular graph, the change in y is the change in position, and the change in x is the change in time, delta d over delta t. Okay, so on a position versus time graph, my slope represents the velocity of the object. Okay, everybody okay with that? That's, again, that's not something I want you to memorize. That takes no time at all to figure out. Okay? Now, sometimes people teach you this formula for slope. Okay? Rise over run. In physics, we don't like that. Okay? It only calculates slope. We like to have formulas that do better. Okay? So what we use is this. Y equals m times x plus b. Probably want to write that down. Okay, so y in that equation is the vertical value of any point on your line of best fit. Okay, so this line would be our line of best fit.
For slope, so it's d minus initial position minus.
I want you to not look at this formula right now.
Okay.
Okay, I'm going to show it better here in a minute. Okay, m is the slope. Okay? X is the horizontal value of the same point on your best fit line. Anybody know what B is? This is B right here. B is what we call the y-intercept. Okay? The y-intercept is basically our initial y value. It is the value of y at the beginning of the graph when x is 0. Okay, now we're going to practice our algebra skills a little bit. So I've got this formula, y equals m times x plus b. Okay? I want to manipulate this formula so that it solves for m. What should I move first? I should move b, because b is not attached to m. Remember, that's the third rule of algebra, the one we haven't used until today. Okay, b is not attached to m, so I'm going to move it first. Right now I'm adding b, so if I want to move b to the other side, I need to
Subtract.
okay, and then what I do to one side, I do to the other. So, subtract b from both sides, b is gone from that side, y minus b equals m times x. I want to get m by itself. What do I do with x?
Divide both sides by
Divide both sides by x. Okay. Okay, so y minus b, is that the rise? It is. Okay, if we go back to our graph here, okay, we said that this is b and this is y. Okay, and then it says over x, right? The way we manipulated that is y minus b over x. Well, is this value right here the horizontal value for that same point? All of x? Okay, I mean, technically I should say x minus 0, because what's x here?
0.
0. That's why we don't write it, because it's 0. Okay, but did I just basically do the same thing? Did I get rise over run using a different formula? Okay, so you're probably going, so why, Coder? You just got slope using that formula. Well, here's why. This formula is easier to manipulate than that one, and it can solve for way more. And we can use it to do something called extrapolation. That means I can use it to calculate stuff that happens beyond the graph. Okay? Let's say that this graph here only goes up to 10 seconds. If I know what m is, and I want to find out where the object will be, its position, at 1 minute, could I substitute 60 seconds in for x and solve for y? I could, because I'd know what b was. I'd be able to read it here. Okay, I'd know what x was. It was 1 minute or 60 seconds, and I'd know what the slope was. So I'd be able to calculate a value that's not on the graph using the line on the graph. Okay, that's something that's not as easy to do with rise over run. Okay, that's why we don't use it. We want to be able to extrapolate for things that are beyond the graph, something we're going to learn more about on Wednesday. Okay, could I also use this formula if someone asked me, how long would it take for the object to reach a position of 100 meters? Yeah, then they'd have given me y. right? Because position is on the y-axis, so they gave me y, and then I'm gonna work to get x by itself. Just algebra, okay, but I can do it. So we use y equals mx plus b a ton, okay? Because it's easy to manipulate, way easier than the other one, and it calculates more. Okay, we can do more with it. Okay? All right. Time we got here. I'm gonna give you guys a 5-minute break and then we're gonna talk about this graph here. Okay, still a position time graph. Okay, I'm gonna give you a little break and then we're gonna talk about this position time graph. So, same kind of questions I would ask you on a quiz or a test about a graph like this. What is the object doing in part A?
Moving at a constant velocity.
Moving at a constant velocity. I want one more thing. Forward or backward? That's what I would want, right? If you say constant velocity, you've got to give direction. Okay, moving at a constant velocity in a forward direction. Okay, what's it doing in B? Stopped. Yeah, I would say stopped is better than nothing. Okay, nothing saying it's not reading a book. Okay, so stopped technically is the correct answer for that. Okay, what's it doing in part C?
Backwards.
Okay, moving backwards at a constant velocity. Okay, what's it doing in D? Stopped. Where is the object moving faster? E or F?
E.
Ooh, we're not so sure about that one. Okay. In which one do you cover more distance in the shorter space of time? E. E is steeper. Did we not just cover that velocity is the slope of a line on this type of graph? That means the steeper the line, the faster it's going. Okay? So in this case, E is the faster section because the line is steeper. And steepness represents the rate at which you change your position, meters per second. Okay? Would that have a higher meter per second value than F?
Yes.
Definitely. Okay, here's what I want you to calculate for me, and this shouldn't take very long. I want the total displacement of this object and the average velocity over the whole trip.
0.
Yeah. 0. Starts at 0, ends at 0, doesn't matter how long it takes. You did not change your position over the whole trip. Okay. I want you to calculate for me the total distance traveled by this object. That's going to take a little longer. Okay, and we're going to assume that there's also a little flat part right here and that this ends at 18 seconds. Okay? So I want the total distance. So how far does this object go? Are you going to have to look at each part of the graph individually here?
Yes.
Okay, that's your hint. Okay, you may have to look at each individual part of the graph. Okay, each time the line changes direction is a new part. Okay, see if you can figure out how far it goes. Okay, just hang on. If you know the answer, just hang on. Okay, who thinks they got it? Okay, what do we get for a number?
32.
32? Okay, So how did we figure that out? Well, is distance scalar or vector? Scalar. So it only cares how far. Right? Can we figure out how far the object goes in each part of this graph? Okay. So in part A, it goes from 0 to 6. How far? 6 meters. Okay. I'm going to put a positive beside that. It's not going to matter for distance, but just out of habit, I put that. Okay. How far in B?
0.
Okay. And then in C, we start at 6 and go to -10. 16. Did you go final position minus initial position to figure that out?
No.
You think you didn't, but you did. That's the only way you get 16 is to go -10 minus 6. You may think you did it another way, but that's what you did in the end. Okay, is you went final position, -10 minus 6, and you got -16. Okay, you may have just added them together, you got 10 on the negative side, 6 on the positive side, but that's the same thing. You still did final position minus initial position. All right, so -16 meters here. How far in D?
0.
Okay, since I'm only caring about the total distance, can I just go from D back to the x-axis here?
Yeah.
I mean, I could do E and then do F, but why? 10 is lots easier. Okay, you go positive 10 meters during that part. All right, so 10 plus 16 is 26, plus 6 is 32. Okay, we went 32 meters in total. All right, assuming the whole trip takes 18 seconds, what's the average speed? You should have your calculator. Okay, assuming the whole trip takes 18 seconds, what is the average speed of the object?
Answer?
Yeah.
Isn't it just 2 meters per second?
Nope, 32 divided by 18 is not 2.
Or sorry, no, it'd be
1.7? Yeah. Okay, so here's what we did, guys. Is speed total distance divided by total time? Okay, you just did all the heavy lifting. You found that the total distance was 32. Okay, and I told you assuming the whole trip takes 18 seconds, okay, total distance divided by total time. Do we use the same formula on a graph as we do on a word problem? That's because the formula came from the graph in the first place. Okay, we actually use it on a word problem even though it comes from a graph. Okay, so that should be about 1.7 meters per second. Do I need a vector on that? No. Is that the kind of thing I might ask you to do? Absolutely. Okay, like your next quiz, that is absolutely the kind of thing I would put on there. A graph that looks like that and ask you a few things like that, like what's going on in part A? What's the total distance traveled? Okay, what's the average velocity? Asking you to do those same kind of calculations you did with the word problems, but now with a graph. Okay, not too tough, is it? Okay, here's a tricky one. Still a position versus time graph. What's the object doing between 0 and 8 seconds? It's accelerating. How do we know that?
Because the slope gets steeper.
Right. The slope gets steeper because it's a curve. Now, are there also curves where the slope gets smaller?
Yes.
Yes. Okay, so as long as we understand that a curve means that this thing is changing non-uniformly, okay, we can quickly analyze it. Yeah, in the first 2 seconds, it only went this far. But in the next 2 seconds, it went further. Same thing we did on that other graph, right? It goes further and further and further each time interval. It's definitely going faster. Okay, so I'm going to go back to this, the lines getting steeper idea. I'm going to teach you the only thing I understood in university calculus. It was the first day. I understood nothing after that. I passed university calculus by memorizing the examples in the textbook and writing them down on my final exam and getting part marks for method. It was graded on the curve. That's how I passed. Fortunately, in my class, there were enough people dumber than me, okay, to help me surf the curve instead of getting crushed by the wave, okay, which happened to me in psychology, right? So in university with the curve, in my university, it was graded out of 9. Everything was out of 9. Okay, you got 4 out of 9, you passed. I got 5 out of 9 in math, even though I had a 51. Okay? I had 94 in psychology. I got a 4. See, that's crushed by the wave. There were enough people who got 100% in that class that 94 wasn't a very good grade. So you're graded not by how well you do, but by how well you do compared to everyone else. It can be great, like it was in calculus, and it can be terrible, like it was in psychology. Okay, ended up passing both, because 4 was a passing grade. Right? Yeah, so just keep that in mind. If you're ever graded on the curve, you only have to do better than half the people to pass. Even if that's a fail, because that actually happened to me as well. Organic chemistry 235. I got 51 in the lab, 37 in the course. I got a 4. So there were enough people who did worse than me that I still passed. Because it wasn't about how smart I was, it was about how dumb everybody else was. So yeah. There's a real flaw in that type of grading, just so you're aware. That's why we don't use it. And there's a real flaw there.
The university is just a competition.
Oh, absolutely. It's a money grab, too. Okay. So, the first day of university calculus, this is what I learned. To a mathematician, a curve is an infinitely large number of infinitely small straight lines strung together. Each line has a slightly different slope. On this curve, those slopes would be getting steeper. Okay? So to a mathematician, when they see this curve, what they see is like what you would see if you were looking at a low resolution picture on your computer. What can you see if the resolution is really low?
Pixels.
You can see the pixels. Okay? Now, in a high resolution picture, the pixels are so small that you can't resolve them with your own eyes and the picture looks really sharp. Okay? So when a mathematician looks at this curve, they don't see a smooth curve, they see all these little straight lines all strung together. Okay? And each one of those lines is getting steeper and steeper. Now, what's going on here in part, well, let's say between here and here?
And it slows down to a stop
It slows down and it comes to a stop. How do you know it comes to a stop?
because it peaks.
Okay, peaks. Okay. Here's the other thing. We're never going to ask you to do this simply because it's really, really hard to grade because everyone's going to get a slightly different number. But according to a mathematician, since this curve is made up of an infinitely large number of infinitely small straight lines, I could draw a line that is tangent to the curve at any given point and calculate the velocity of the object at that instant by calculating the what of that tangent? The slope. Okay? If I calculate the slope of that tangent, that's the velocity of the object at that point, because I've just drawn a line that's parallel to the curve, to that tiny little line at that one particular point. Yes. So, back to this idea of how fast is it going, or does it come to a stop here at B? Okay? Yes, it does. Because if I draw a tangent at B, what's the slope of that line? 0 is horizontal. Okay? So at that point, at B, the object is actually stopped for an instant. Okay? Then what does it do right after that? Right, does it get faster and faster? Yeah, it gets faster and faster till here. Then it gets
Slowly.
right, because the slope starts to decrease or flatten, right? The curve starts to flatten out. Okay? What is this a graph of?
A roller coaster. Oh.
It's a graph of somebody throwing anything up in the air. During part A is when I'm accelerating the marker with my hand, pushing it upwards. Once it leaves my hand, I'm not moving it anymore. What's acting on it?
Gravity.
And gravity causes it to slow down, right? What goes up?
Must come down.
Exactly, so gravity slows it down, slows it down, slows it down, it stops for an instant, and then it accelerates back down to the hand, which slows it to a stop. I would never ask that on a test. That is completely unfair. Okay, give you a graph and go, what is this a graph of? Okay, now, would it be fair to say, what is the object doing in part A? Absolutely, that would be fair. But to ask you to pull out of a hat, what is this? Okay, that's not really fair. But can you see now that this would be an object being thrown up in the air? Okay, that's why the two halves of this motion here are mirror images of each other. The acceleration due to gravity is the same when the object is moving up and when it's moving down. Gravity always accelerates objects at 9.81 meters per second squared. Okay, so in this case, as it was moving up, it was slowing at 9.81 meters per second squared. And then it accelerated back down to my hand at 9.81 meters per second squared. That's why the two parts of that hump are mirror images of each other. The object was doing exactly the same thing in both. The only thing that was different was in one it was moving up and the other it was moving down. Okay, does that sort of make sense?
Mhm.
Okay, so that's the kind of analysis we want to be able to do of a graph. Okay, so look at it and be able to say, in this part of the graph, the object's slowing down because the curve is flattening. Okay, that means its change in position is decreasing. That means it's going slower. Okay, being able to do that kind of analysis rather than it's a curve, so it's accelerating. Okay, we want to have that other level of analysis there. Okay. Okay, we're not going to do velocity time graphs. Or my position time graphs. Okay. So, I would like you guys to try this question. Using that position versus time graph, I want you to calculate the total displacement, which is not in meters per second. Oh, come on. Okay? Those are the answers, so you can check and see if you did it right. Okay? And I want you to calculate total displacement, total distance, average velocity, average speed for that graph. If you're having trouble seeing it, just come up a little bit closer to get the numbers. Okay, so if I want to find the total displacement, is this a good way to go about calculating total displacement? Final position minus initial position.
Yes.
Okay, so my final position is 0.5 meters. The initial position is 0.2 meters, so our displacement is positive, 0.03 meters. Sorry, 0.3 meters. Man, it is definitely feeling like a Monday. 0.3 meters. Okay, and then total distance. Well, then I got to do each part. What's the distance here? Nothing. Okay, then I go from 0.2 to 1, so that's 0.8. Then nothing, and then from 1 down to 0.5, so that's 0.5, 0.8 plus 0.5 gives us 1.3 meters. We don't care for distance, whether we're going forward or backward. Okay, have we done all the heavy lifting already for C and D?
Yes.
Yes. Okay, so for C, okay, we're looking for average velocity, total displacement over total time, 0.3 over 7 seconds should give us positive 0.04 meters per second. The positive is important. Okay, and then average speed, okay, B equals D over T, 1.3 divided by the total time, which was 7 seconds, and we get 0.19 meters per second, no vector. Okay, so that is exactly the kind of thing I would ask you to do on a quiz. And an exam. Okay? All right, good job today, guys.
Thank you.
Welcome.